So next we will see the derivation for the components of TM mode in a rectangular waveguide. Now we have equation 1, 2, 3 and 4, that is for ESX, ESY, HSX and HSY for a rectangular waveguide, and you can see the derivation for equation 1, 2, 3 and 4 in the PDF title, derivation for rectangular waveguide. Okay. So these are the components of ESX, ESY, HSX, HSY, where H square is equal to gamma square plus omega square mu epsilon, where gamma is your propagation constant. Now for Tm we know HSZ is equal to 0. So what I am going to do is I am going to apply this condition in equation 1, 2, 3, 4. That is substituting HSZ is equal to 0. So what happens, my components become ESX is equal to minus gamma H square dou Ez by dou x, ESY is equal to minus gamma H square dou Ez by dou y, so and so. Simply you substitute HSZ is equal to 0 in 1, 2 and 3 and 4. So now this is my equation 5, 6, 7 and 8. Also we have derived the expression for ESZ, that is equal to E naught sin m pi x by a into sin n pi y by b exponential minus gamma z, that is equation 9. Now in the next step, what I am going to do is I am going to differentiate this equation 9 with respect to x and with respect to y, that is my equation 10 and 11. I am simply differentiating ESZ with respect to x and y, and after that what I am going to do is I am going to substitute 10 and 11 in 5, 6, 7, 8, because here you have the terms dou ESZ by dou x, dou EZ by dou y, etc. Right. So for that I am differentiating E with respect to x and y, and I am substituting in 5, 6, 7 and 8. So finally I will get my components ESX, ESY, HSX and HSY, that is B, C, D, E. So finally I can say A, B, C, D, E. A is this one, which A is this one, A, then B, C, D, E are the components of TM wave. Now as I said earlier, H square is equal to gamma square plus omega square mu epsilon, which can be written in terms of Ka and Kb. K and Kb means this one, Kb m pi by a and n pi by b, that is equal to Ka square plus Kb square. Okay, H square is equal to gamma square plus omega square mu epsilon, which is equal to Ka square plus Kb square. So from that gamma square I am writing it as H square minus omega square mu epsilon. So gamma is equal to square root of H square minus omega square mu epsilon. We know H square is also equal to what? Ka square plus Kb square. So I can substitute H square as Ka square plus Kb square, then minus omega square mu epsilon. Then what is K and Kb? M pi by a and n pi by b. I am substituting it, and that is my equation 12. And we know that gamma can also be represented as alpha plus j beta, where alpha is your attenuation and beta is your phase shift constant. Now if we assume that the inner surface of the rectangular waveguide is a perfectly conducting medium, that means this area, the darkened portion, it is a conductor, and I am assuming that it is a perfect conductor, then I can say alpha is equal to 0 in case of a perfect conductor. So I am substituting alpha equal to 0 in equation 13, so that I can write gamma is equal to j beta, which is a complex quantity. Now that means if the wave should propagate with no attenuation, then my gamma value, that is the propagation constant, should be a complex number, right? Because here you know the propagation constant gamma is equal to alpha plus j beta. So when I substitute alpha is equal to 0, I got alpha is equal to j beta. That means if alpha should be equal to 0, then the gamma value should be a complex number. And this is possible if and only if in this equation 12 this term omega square mu epsilon should be greater than the rest of the two terms, that is m pi by a and n pi by b, right? When this term omega square mu epsilon is greater than the remaining two terms, then it's clear that gamma will be a complex quantity. So I can write, if the wave should propagate with no attenuation, gamma should be complex, which is possible if omega square mu epsilon is greater than m pi by a the whole square plus n pi by b the whole square in equation 12. Okay. So therefore equation 14 using equation 14 and equation 12, I can write what is gamma. Gamma is equal to, I can write, equation 14 and 12, I can write beta is equal to square root of omega square mu epsilon minus m pi by a the whole square minus n pi by b. Right, because here it is gamma. Gamma means it is equal to j beta, right? I am substituting j beta, that is just removing the beta term. So beta is equal to what? I am slightly rearranging the term as omega square mu epsilon minus m pi by a the whole square minus n pi by b the whole square. So why I am writing it is, see here, earlier we arrived at the condition that if a wave has to propagate through a waveguide without any attenuation, then this term omega square mu epsilon should be greater than what? This term. Okay. When this happens, that is when omega square mu epsilon is greater than this term, what happens? The term gamma becomes a complex term, that is gamma is equal to j beta. So that is why we have written here beta is equal to square root of omega square mu epsilon minus m pi by a the whole square minus n pi by b the whole square. So this particular value, that is this equation 15, will be a real quantity because omega square mu epsilon is larger compared to other two terms. So beta will be a real term, and that value we can substitute in equation 14, that is gamma is equal to j beta, so that gamma becomes a complex term. So that is written here in equation 15, beta value is real and therefore the gamma value becomes complex since gamma is equal to j beta. Now the lower limit of angular frequency, that is omega c, is called the cutoff frequency, below which the propagation is absent. Okay, I already told that cutoff frequency is a minimum frequency for propagation and below frequency will not be propagated. And now this is possible only when gamma is equal to 0. That means the propagation constant will be 0 for all values of omega which is lesser than omega c, right? So what I am going to do is omega square, here I am taking the condition omega square mu epsilon is equal to m pi by a the whole square plus n pi by b the whole square, that is written here omega square mu epsilon is equal to m pi by a the whole square plus n pi by b the whole square, and instead of omega I am writing it as omega c square. Okay, omega, because here we are considering the cutoff frequency of waveguide, below which there will be no propagation taking place. Okay, that means here you can see, if you substitute gamma equal to 0 in this expression, you will get omega square mu epsilon is equal to m pi by a the whole square plus n pi by b the whole square, and instead of omega I am simply substituting omega c square. From that omega c is this expression. If you know omega c, you can find out fc, and that is the second one, and also you know 1 by square root of mu epsilon is c, that is this term can be equal to c, and this is the expression for your cutoff frequency. Similarly, the corresponding cutoff wavelength is given by lambda c is equal to 2 divided by square root of m by a the whole square plus n by b the whole square. And also we know that the phase velocity Vp is equal to omega by beta, where omega divided by beta value we know, that is omega square mu epsilon minus m pi by a the whole square, minus n pi by b the whole square. That is my equation 17. Then I can use equation 16 in 17, that is 16 is this one, that is omega c square mu epsilon is these two terms. So instead of that term we can substitute omega c square mu epsilon here. Instead of these two terms I can substitute omega c square mu epsilon, and the first term remains the same, that is omega square mu epsilon. So slightly rearranging the expression, finally I will get 1 by square root of mu epsilon into 1 minus omega c by omega whole square root. So from that you will get the expression for for your phase velocity Vp. Okay. Next we will see what is a guided wavelength. Wavelength within the guide is called guided wavelength, which is often notated as lambda guided, and it is a ratio of the velocity of waves in the guide, that is Vp to frequency f. So I can define guided wavelength lambda is equal to Vp by f. Vp we already know, that is c by square root of 1 minus fc by f the whole square. Then this f is this one, which finally you can modify and write in terms of lambda naught, where lambda naught is equal to c by f, that is this term. So lambda naught by 1 square root of 1 minus fc by f the whole square, and the same term, that is lambda guided, can be expressed in terms of wavelength as lambda naught by square root of 1 minus lambda naught by lambda the whole square. So that's the derivation for lambda guided. And finally this relation is also important. This is a relation connecting lambda naught, lambda c and lambda guided. That is 1 by lambda naught square is equal to 1 by lambda square guided plus 1 by lambda c square. And that's all in this slide, and thank you.